Welcome to today's deep dive. Today, we are actually doing something a little bit different.
Yeah, we have a really great setup for this one,
We do. We are going to be walking you through a fascinating 15 slide masterclass on geometric optics.
which sounds intimidating, I know, but it's really not.
Right, exactly. The mission today is specifically designed for absolute beginners. We want to completely demystify the core physics of light, figure out exactly how it behaves when it hits different boundaries, and really just understand the hidden math behind everyday optics.
Yeah, it's all about looking at the things you use every day, mirrors, glasses, whatever, and understanding the actual geometry making them work.
So, to make this as clear as possible for you, we are going to be walking through this presentation slide by slide.
Kind of an audio tour of the deck.
Exactly. I'll let you know every time we move to the next slide so you can follow along with the structure. So, okay, let's unpack this. We're starting with slide one.
Right, slide one.
The title is Geometric Optics, the Path of Light. And well, the first thing it does is establish the absolute foundational physics principle for everything we're about to talk about.
Which is that light travels in perfectly straight paths. We call them rays, right up until it hits some kind of physical boundary.
And this slide promises a full visual masterclass in reflection, refraction, spherical boundaries, all of that. But I do have to ask a question right off the bat, just to push back a little.
Okay, go for it.
Well, every time we hear about advanced physics or quantum mechanics, we're told light is a wave, right? Or like a probability cloud. Does this slide basically mean we are literally treating light like a straight line from a high school math class, just totally ignoring the wave-like nature of it?
Honestly. Yes.
Yeah.
And that's exactly the beauty of geometric optics.
So we just ignore quantum physics.
Well, I mean, light absolutely has a wave-like nature, but you have to think about the scale. At the macroscopic scale, like when we're dealing with car mirrors or glass lenses, the wavelength of light is just so incredibly tiny compared to those
Oh,
objects.
I see.
Yeah, so the wave effects essentially vanish for our purposes. Treating light as a straight geometric line isn't a lazy shortcut. It's a highly precise mathematical model. It lets us actually engineer things without getting bogged down in quantum chaos.
That makes a lot of sense.
Hmm.
So, to understand where these lines of light are going, we really need a map of the territory, right? Which brings us to slide two.
Setting the stage.
Right, setting the stage. The two zones. This slide divides the entire optical universe into two distinct sides.
Yeah, you have zone one, which is the incoming light side, and then zone two, which is the outgoing light side.
And there's some serious math introduced here right away. We get this universal blueprint equation. It's 1 over s plus 1 over s prime equals 1 over f, which also equals 2 over r.
Yep, that equation governs pretty much everything we'll talk about.
And there's also the lateral magnification equation. The m equals negative s prime over s. I like to think about these zones like a theater.
But the
Yeah, like zone one is the audience seating. That's where the incoming light is, where the physical objects actually originate. So mathematically, that's a positive space. The S is greater than zero.
okay, I tracked
And
it.
then zone two is like backstage, it's where the light is trying to go. But the slide points out something really weird here. It says virtual images are formed back in zone one, meaning the S prime is less than zero.
Right, virtual images.
I have to ask, does virtual just mean the light is fake? Like, how is an image forming back where the light came from?
No, the light isn't fake at all. The photons are very real. Virtual just means the light rays don't physically intersect at that spot in space.
Wait, then how do we see an image there?
It's your brain. The rays bounce off a mirror and spread out, they diverge. But your visual cortex assumes light always travels in a straight line.
So it traces them backward.
Exactly. Your brain traces those spreading rays backward to a point behind the mirror where they look like they came from. That point is the virtual image. The light isn't fake, but the intersection point is basically a neurological illusion.
Wow. Okay, so now that we have our blueprint and we understand these two zones, let's actually see what happens when light hits a boundary and bounces back. We are moving to slide three.
Act two of the masterclass, bouncing light.
Right, focusing on reflection via concave and convex mirrors. And here's where it gets really interesting for me. The slide details four very specific color coded rays.
Yeah, the visual on this slide is fantastic.
It really is. You've got the parallel ray in cyan, the focal ray in magenta, the radial ray in amber, and the central ray in green. But practically speaking, if I'm just trying to find where an image forms in a mirror, do I actually need to draw all four of these distinct rays?
Oh, not at all. You only ever need two rays to find an intersection point.
Then why map out all four?
To prove the physics.
Yes.
It demonstrates the absolute flawless geometric symmetry of the mirror.
Ah, I get it.
Yeah, no matter which of those four completely different paths the light takes, whether it bounces through the focal point or hits the vertex directly, they all perfectly converge at the exact same coordinate. It's the universe proving its own math.
That's incredibly satisfying. Let's take these bouncing rays and actually apply them to a real world object for the listener. Next up is slide 4.
Applications.
Right. Slide 4 and 5 are all about mirrors in action. On slide 4, we're analyzing a convex mirror with a little light bulb acting as the object.
And this is where that universal blueprint equation comes into play.
Exactly. The math here gives us an object distance, the ES, of 35.5 centimeters. The focal length is negative 12.2 centimeters, and the height is 4.0 centimeters.
And when you crunch those numbers, the resulting image distance, the S prime, ends up being negative 9.08 centimeters.
Which means it's a virtual image, right?
Uh,
Because it's negative, it's on the incoming light side.
Yep, it forms behind the glass.
Yeah.
And the magnification tells us it's upright and reduced to just about 1 centimeter tall.
This is exactly what I wanted to connect to the listener's everyday life. This specific math, right here on slide 4, is the exact physics behind the passenger side mirror on your car.
Oh, absolutely.
It's a convex mirror. It shrinks the image down so you get a wider field of view. And that is exactly why it says objects in mirror are closer than they appear.
It's not just a warning, it's literally describing the geometric optics of a reduced virtual image.
I love that. Okay, transitioning to slide 5. Now we're looking at a concave projection. The goal in this slide is to project an image that is 2.25 times the object size onto a wall that is 4 meters away.
Right, so we want a real image here.
Yes, and since real images are always inverted, the magnification is negative 2.25. The distance between the image and the object is 4 meters. When we run the math, the object has to be 3.2 meters away from the mirror.
And the image forms at 7.2 meters, which means the mirror itself needs a radius of 4.43 meters to make this work.
It's just so cool that we can calculate that exact physical shape.
Well, if we connect this to the bigger picture, this is exactly how humanity manipulates light.
What do you mean?
Think about car headlights or movie theater projectors. You place a bright light source at a very specific mathematical distance from a concave mirror, and it catches all that light and blasts it out into the physical world as a focused, real image.
So it's taking the mathematical theory and making it a physical tool.
Exactly.
Okay, so we've seen light bounce, but what happens when it passes entirely through the boundary? Let's bend some light on slide 6.
Act 3, thin lenses.
Right. Slide 6 introduces refraction through thin lenses. So we're looking at converging, which are convex, versus diverging, which are concave. The core physics completely changes here because the light passes into zone 2 instead of bouncing back into zone 1.
Yeah, the light is transmitting, not reflecting.
But hold on. I spotted what feels like a massive trap for beginners on this slide.
Uh-oh, what's that?
Okay, wait. A convex lens converges light, right? It brings it to a point.
Right.
But just a few slides ago, we established that a convex mirror diverges light. It scatters it. That seems deliberately designed to confuse us.
It really does. I know, it trips up a lot of students. But it comes down to how the physical shape interacts with the medium.
Explain that for us.
So a convex mirror bulges outward. So when light hits the outside of that bulge, it bounces off at diverging angles. It scatters.
Okay, that makes sense for bouncing.
But a convex lens is made of glass. Light actually slows down when it enters glass. Because a convex lens is thickest in the middle and thin on the edges, the light hitting the middle is delayed more than the light on the edges.
Oh, so the edges move faster and sort of pivot inward?
Exactly. That differential in speed bends the light inward, causing it to converge. So the same geometric shape does opposite things depending on if the light is bouncing off it or traveling through it.
That is fascinating. Okay, let's combine the next two application slides, slides 7 and 8, to see the math on this.
Let's do it.
On slide 7, we have a converging lens. The focal length is positive 10 centimeters, and the object distance is 30 centimeters. The math yields an image at positive 15 centimeters.
And because that number is positive, we know it's a real inverted image on the outgoing light side. It physically exists in space.
Right. And then on slide 8, we look at a diverging lens. Here, the focal length is negative 10 centimeters. Object is at 20 centimeters. The result is negative 6.67 centimeters.
Which means it's a virtual, upright, and reduced image,
Hmm.
trapped back on the incoming side, optically speaking.
Right, exactly. So we keep throwing around these terms, real and virtual. Let's move to slide 9 to permanently lock in what these mean for you, the listener.
This slide is basically the ultimate cheat sheet.
It really is the boundary diagnostic. So real images form on the outgoing side where S prime is greater than 0.
Right.
They can actually be projected onto a physical screen. They are formed by actual intersecting light rays, and they are always inverted, meaning a negative magnification.
Yep, perfectly summarized.
And then virtual images form on the incoming side where S prime is less than 0. You cannot project them onto a screen. They are formed by that perceived backtracing of diverging rays we talked about, and they are always upright.
What's fascinating here is how this really highlights both the limitation and the brilliance of the human eye.
How so?
What, your brain physically cannot tell the difference between actual intersecting photons,
Yeah.
a real image, and diverging rays that just look like they came from a point behind a piece of glass.
It just processes the angles and says, there's an object there.
Exactly. We are completely reliant on our brain's interpretation of the geometry.
That is slightly terrifying, but also really cool. Okay, so far we've looked at thin lenses and mirrors just sitting in the air. What happens when light enters a solid medium, like water? We are moving to slide 10.
Act 4, spherical refractive surfaces.
Right. Slide 10 introduces a slightly scarier equation, the refractive boundary equation. It's no over S plus NB over S prime equals NB minus Na all over R.
It looks complex, but it's just adding the density of the materials into the mix. The Na is the refractive index of the incoming medium, and NB is the index of the outgoing medium.
Like moving from water to air,
Exactly.
which perfectly sets up slide 11. Moving to slide 11, we get to apply this to the classic fishbowl problem.
Well, this is a staple of optics
It
classes.
really is. So the setup is this. A fish is 5 centimeters inside a spherical fishbowl. That's our S. The bowl's radius is negative 15 centimeters.
And it's negative because the center of curvature is back on the incoming side where the fish is.
Right. The light travels from water, which has a Na of 1.33, out into air, which has an NB of basically 1.00.
And when you run all those variables through the equation, solving for S prime gives us approximately negative 4.1 centimeters.
With a magnification of positive 1.1. So what does this actually mean for us?
It means the fish isn't where it looks like it is.
Yes. For the listener, this is why when you look into a fishbowl, the fish appears closer to the glass than it actually is and slightly larger.
By about 10%, according to the math.
Exactly. And it's the exact same physics as when you are standing in a swimming pool and you look down at your own legs.
Oh, yeah. They look super weird.
They look totally stubby and like they're only a few inches below the surface. The water is acting as a refractive boundary, bending the light and feeding your brain a virtual image of your own legs.
It's all just geometry playing tricks on you.
So if we know the exact math of how these different mediums bend light, can we actually engineer our own lenses from scratch? Let's look at slide 12.
The engineer's toolkit.
Slide 12 features the famous lens maker's equation. It's 1 over F equals N minus 1 times 1 over R1 minus 1 over R2.
This is such a powerful equation.
Hmm.
It tells us that if you are in a standard air environment, a lens's focal length is dictated by only two things:
Which are?
the refractive index of the glass you choose to use, the N, and the physical geometry of the two curves you carve into it, the R1 and R2.
Let's see that in action on slide 13. We get to literally design a lens here. We are given a piece of glass with an index of 2.0. We carve a first surface radius of positive 20 centimeters and a second surface radius of negative 35 centimeters.
And the calculation proves that the resulting focal length is approximately positive 12.73 centimeters.
And because that focal length is positive, it functions as a converging lens.
Yep, it will focus light to a real point.
But this brings up a manufacturing question for me. If I'm physically making this lens and I mess up, like I carve the glass backwards, making the first radius negative instead of positive, do I just completely ruin the lens's function?
Oh, absolutely. If you flip the physical geometry, you change the mathematical signs in the equation. A lens designed to converge light could suddenly become a diverging lens.
Just from carving it backwards.
Yeah. It really highlights just how unbelievably precise optical engineering has to be. Your prescription glasses are a geometric marvel.
I will definitely treat them with more respect now. Okay, we have covered mirrors, thin lenses, and glass boundaries. To bring this all together for you, we are moving to the final two slides.
Act 5, the grand summary.
Yes, slide 14 and 15. Slide 14 gives us this massive master matrix table. It basically summarizes the orientation and image types for literally every system we've discussed today.
Plane mirrors, concave, convex, converging lenses, diverging lenses. It's all there.
And then slide 15 is the unified equation board. It groups the equations for plane mirrors, plane refractive boundaries, curved mirrors and thin lenses, and curved refractive boundaries into four perfectly elegant equations.
And looking at this board, it raises a really important, almost philosophical question.
What's that?
Well, for the listener to think about, why do these seemingly completely different physical phenomena share nearly identical mathematical structures?
Like light bouncing off a silver mirror versus light bending through a glass bowl of water.
Exactly. Physically, they are totally different interactions.
Yeah.
But mathematically,
Yeah.
the equations are almost the same.
Hmm.
It reveals this deeply unified, incredibly symmetrical geometry to the whole universe.
It really is a satisfying aha moment to end the masterclass on. Looking at that unified board just makes the chaos of the universe seem so orderly.
It's Fermat's principle at work. Light is always finding the most mathematically efficient path.
So, to summarize the journey you've been on with us today, we started with a simple line of incoming light. We bounced it off mirrors, we bent it through thin luxes and water boundaries, and finally we saw the universal mathematical matrix that governs all of it.
You have officially conquered the absolute basics of geometric optics.
You really have. But before we go, I want to leave you with one final incredibly provocative thought, something that wasn't even covered in the slides, but builds directly on what we just learned.
Oh, I know where you're going with this.
Yeah. Knowing what we now know about converging lenses from slide 7, that they create real inverted images. Well, you should know that the biological lens sitting inside your own human eye is a converging lens.
Yep.
Which means, right now, as you are listening to this, the actual physical image being projected onto your retina at the back of your eye is completely 100% upside down.
It's wild to think about.
Your brain is doing real-time physics calculations every single millisecond to flip the world right side up for you. In fact, if you were to wear special glasses that inverted your vision after a few days, your brain would just passively reinvert your vision to make it normal again.
The brain is the ultimate optical computer.
It really is. Just something to mull over the next time you look in a mirror. Thank you for joining us on this deep dive, and we'll see you next time.